can you see my slides okay? Great.
All right, hello everyone, and welcome back to the final session of this workshop. We're going to kick things off in this session with an invited talk from Rebekkah Dawson on the origins of hot Jupiters. And I can already see your screens up, Rebekkah, so you can take it away when you're ready.
Great, thanks so much. And thanks very much for having me here. I'm really excited to talk to you all today. So since their discovery in 1995, hot Jupiters have challenged our understanding of how planetary systems form and evolve. Although they're intrinsically rare, only about 1 in 100 stars has a hot Jupiter, they're an extreme outcome of processes that likely affect many planetary systems and are missing from our classic understanding of planet formation. I'll start by talking a little bit about that classic understanding and why hot Jupiters are so surprising. So our classic textbook picture of the origins of planetary systems starts with a spinning cloud of gas and dust that collapses into a disk. In the outer parts of the disk, where there's a lot of ices available and where feeding zones are large, a core can grow and accrete a gas atmosphere to become a gas giant. After a few million years, the gas disk goes away and rocky planets form in the inner solar system. So this very simple textbook version, inspired by our solar system, predicts or explains at least a few key characteristics. First is that we have rocky planets in the inner part of the solar system and gas giants further out. We see them all on circular orbits, and the planets are all orbiting in the same plane. But now the planet party has grown from just the solar system to thousands of known exoplanets. And we've had some very unexpected guests. So hot and warm Jupiters, giant planets close to their stars, really defy our expectations of how planets form and evolve. Hot Jupiters, which I'll focus on today, are, instead of being in the outer part of the solar system, 10 times closer to their star than Mercury is to the sun. Planets have been found on highly elliptical orbits, and some that have their spin or have their orbit misaligned from the host star's spin. So even with some of the first exoplanet discoveries, we learned that not all solar systems share these key characteristics, and that there must be some physical processes that are missing or wrong in our classic understanding of how planets form and evolve. So if we focus today on hot Jupiters, knowing that they're an extreme outcome of processes that might affect other systems too, people have come up with 3 general types of theories for how they might originate. First is that maybe despite our expectations, they could form so really close to the star. Another is that they form further out from the star, like where our own Jupiter does. And then during the stage where there's a gaseous disk around the star, that disk drives them in close to the star, which is called disk migration. Then another possibility is that they form further from their star, get excited onto a very elliptical orbit, and then tides raised on the planet by the star shrink and circularize the planet's orbit, which is called tidal migration. And all 3 of these types of theories can lead to a giant planet close to their star. So we need some other information to be able to distinguish between these 3 theories. And now is an exciting time where we have 400 or more confirmed hot Jupiters, and we can start to test these theories using other properties of hot Jupiters. Some of the properties that we can look at are properties of the hot Jupiter itself, like its radius or atmosphere, properties of its orbit, so its eccentricity, some major axis, the overall hot Jupiter occurrence rate. We can look at properties of the star, like age, obliquity, and metallicity. We can compare hot Jupiters to warm Jupiters and to smaller hot planets. And we can look at hot Jupiter's companions, both nearby and further out in the system. So we have a review where we looked at all the evidence that we could think of about hot Jupiters and tried to compare it to these 3 different origin scenarios. And we made this giant table that I'm not going to go through in detail, but basically we take each piece of observed evidence, which I'll talk some more about different ones of these in a few minutes, and we assess for in situ formation, disk migration, and tidal migration. Is it consistent? Check. Is it inconsistent? X. Or do we need more information, which would be O or T? And all I want you to take away from this table is that there's no theory in situ formation, disk migration, or tidal migration that has all checks or all X's. And this is some evidence that there may be more than one origin of many of the hot Jupiters we see. Some come one way and some come another way. So now let's look at a few examples of some of the most constraining observational evidence for the origin. So let's first look at their orbital eccentricities. Orbital eccentricities are helpful because it can trace different processes that result in different eccentricities. In particular, if we think about where does the planet fall in the distribution of eccentricity versus semi-major axis, there are different physical processes that populate different parts of this parameter space. So planet disk interactions, like the gas disk migration we talked a bit about, can move a planet further or closer to the star, but usually under most disk conditions isn't going to raise the eccentricity very much. Planet-planet scattering, 2 planets having a gravitational encounter, can drive up the eccentricity, but is more effective further away from the star. Then high eccentricity tidal migration, that other origins channel we talked about, in that case, you get the planet's eccentricity excited, maybe by gravitational interactions with another planet or a star. And if it's eccentric enough, that's when the tidal migration kicks in. And so that can move planets through this red part of parameter space. And there's a lot of parameter space where only high eccentricity migration is populating it. If we see a planet in this red region, based on our current understanding, only high eccentricity tidal migration is a good explanation. So when we see planets here, it's some strong evidence that high eccentricity tidal migration is at work. So if we then put the observed population of planets on this plot, and particularly hone in on planets with some major axis less than 0.1, which we can call a hot Jupiter, we can see that there are indeed a number of planets in this red region. They have high eccentricities, and those eccentricities are too high based on our understanding to have been excited by the disk or by planet scattering. So the best explanation for that is high eccentricity tidal migration, that these planets formed further out, got put onto an elliptical orbit, and are tidally circularizing and are finishing up that tidal circularization process. So tidal migration is not the full story though, and we can get hints of this as we try to look at other properties. So now let's think a bit about the host star metallicity. There's a well-known correlation between having a giant planet and having a more metal-rich stars. The more metal-rich stars have a higher occurrence rate of giant planets. So if we go back to this observed plot, I'll now tell you what the red and blue symbols mean. Red means that it orbits a star that's more metal-rich than the sun, and blue means it's more metal-poor. And so we can see of these eccentric hot Jupiters that I said very likely came from high eccentricity tidal migration, they tend to be orbiting the more metal-rich stars. But that's in contrast to the overall population of hot Jupiters, where we see some are orbiting more metal-rich ones and some are orbiting more metal-poor. So this raises the possibility of multiple origins channels. So one possibility is that this high eccentricity tidal migration process only happens around the more metal-rich stars. Maybe it needs other giant planets in the system, and you're more likely to have these multiple giant planets when the star is more metal-rich. Then in contrast, maybe disk migration and in situ formation could happen around metal-rich or metal-poor stars and explain other hot Jupiters that didn't come through the high eccentricity migration channel. We get some other hints of there being more than one origins channel at work when we consider nearby companions to hot Jupiters. So if planets undergo high eccentricity tidal migration, we don't really expect them to have any nearby companions because this process likely would have wiped out or destroyed or collided anything that was along the way for the hot Jupiter. But in situ formation or disk migration, you could have nearby companions that either migrated together or formed after. So if we see companions, it's more in support of one of these two scenarios. So what people have found is that most hot Jupiters do lack nearby companions, which is in contrast to other types of planets. And so that implies that high eccentricity tidal migration could be a good explanation for these. On the other hand, there are a couple exceptions. For example, WASP-77b has two nearby smaller planets, which is not easily compatible with high eccentricity tidal migration. So this would be a lot more compatible with disk migration or in situ formation. So this is another hint that there may be at least two different ways that we're getting a substantial number of hot Jupiters. So that's a couple examples from this table. So that some of the examples that I've shown so far are kind of pretty strong and clear evidence. Maybe some people have different opinions, but at least among the evidence we have, that's some of the more straightforward evidence. But you can see some of these pieces of evidence. We'll talk about atmospheres later. We're going to talk about obliquities now. They don't have checks or X's. They have like O's and T's, and that means that there's still uncertainty in either the observations or on the theory side, which of these explanations are compatible. So one such category of ambiguous evidence is the obliquity of the host star. So is the star aligned with the planet's orbit, or is the star's spin misaligned? We talked at the beginning about there being a population of planets with orbits that are misaligned from the host star's spin. The most naive explanation would be that that measurement would reflect the origins of the planet. So very simple preliminary idea would be that in situ formation or disk migration would keep everything nice and aligned, but that high eccentricity tidal migration might cause misalignments because the same processes that excite the planet's eccentricity often lead to or require a large mutual inclination between planets that might get reflected in misalignment from the host star's spin. Unfortunately, it ends up being a lot more complicated though than this simple diagnostic. So turns out to be many physical processes that can excite the obliquity either before the planet even forms or afterwards, leading to ambiguity in the interpretation. So before the planet even forms, we can have the disk get misaligned as the star is accreting. We can have magnetic warping of the disk. We can have the disk get misaligned from the star as it disperses if we have an inclined star and there's a resonance crossing. Then after the planet forms, we could have some of the same processes that lead to high eccentricity tidal migration, like secular chaos, planet-planet scattering, or cyclical Kozai leadoff cycles that periodically excite the eccentricity. That's kind of the original interpretation of being misaligned. But we could also have obliquities get excited as the star spins down. There may be another resonant crossing. That's where frequencies in the system are changing. And when they get passed through very similar frequencies, you can excite the obliquity. So seeing a misaligned planet doesn't necessarily tell us that one of these three processes occurred, because there's a lot of possibilities either before the planet even forms or after it forms. Making it even more complicated, there's strong evidence that tidal realignment has erased many of the obliquities. So this is a plot of the projected obliquity, which is what we measure for most planets, not the full angle, as a function of an estimate of the tidal dissipation timescale. And now the tides are tides raised in the star that could realign the planet or realign the star, however you want to think about it. And we can see that when we look at stars that have relatively short tidal dissipation timescales, their planets tend to be aligned. And when we look at the longer tidal dissipation timescales, we see a broad range of misalignments. So this is some evidence that tides on the star might be realigning the star, and that when we see an aligned planet doesn't mean that it was always aligned, and it may not really trace the origins channel. So we've seen now some evidence for there being multiple origins channels, both because some pieces of evidence seem to fairly clearly reflect the need for two origins channels. And then there's other evidence where we can't really distinguish between the origins channels. But if we go with the idea that there are multiple origins channels at work, what I now want to focus on in the talk is, first, what other types of planets share these origins channels, and what additional constraints do they provide on understanding the origins of hot Jupiters? And in particular, we'll take a look now at hot Neptunes, smaller planets that are really close to their star, and warm Jupiters that are further out, though still pretty close in compared to what we expect. Then at the end, we'll talk about probably what's of most interest for this workshop. What are the consequences for the planet's atmosphere? So let's first take a look at this first question of the other types of planets. So there's been some relatively new and strong observational evidence that hot Neptunes often share the same properties as hot Jupiters. One property they share is that they typically lack nearby planets, at least transiting nearby planets for hot Neptunes. So this is a plot of planet radius versus orbital period, and the color of the planet tells you, is it a single transiting planet or are there multiple transiting planets detected in the system? This comes from the Kepler mission. You can see hot Jupiters are blue, so they're the only transiting planet observed in the system. Small planets, there's reds and blues, so some of them have other transiting planets. But these hot Neptunes between 2 to 6 Earth radii also tend to more be blue. So they also tend to be singles and to lack nearby planets, which either means they're alone in their system or that the other planet is in a different plane, so it's not transiting. There's another piece of evidence is that hot Neptune host stars seem to have similar metallicities to hot Jupiter host stars. So here is a cumulative distribution of metallicities for the stellar sample, other smaller hot planets, and then in pink is hot Neptunes and in green is hot Jupiters. And Dong et al. Find that hot Neptunes have the same elevated host star metallicities as hot Jupiters. So this is cool because now we can, as we investigate hot Neptunes, we can kind of keep in the back of our mind that they might share the same origins as hot Jupiters and that some of the results might be applicable to both. So one cool system that some of us have recently characterized is the Pi Mensae system, which has an inner hot Neptune and then an outer planet or brown dwarf who has Gaia measurements that help us get the full 3D orbit for that planet. And what we and others have found is that there's a significant mutual inclination between the hot Neptune and the outer planet in the system. And even though it's not completely pinned down what exactly that inclination is, it's definitely a significant mutual inclination and misalignment. And this is really cool because for a lot of those hot Jupiter systems we talked about that were misaligned with their star, we don't actually know if they're misaligned with some other planet in the system. And that makes it ambiguous whether the whole disk got misaligned or whether it's a misalignment between planets that's more of a high eccentricity tidal migration type scenario. So in this case, we see the planet is misaligned and simulated some possible origins. One might be high eccentricity tidal migration for this hot Neptune. There's a caveat that maybe the whole inner system is getting mutually misaligned and that maybe these planets did form, maybe the inner planet did form close to its location. We can't know just from the system exactly what its origin was, but it is cool to see an actual misalignment, which for most systems is not something that we can measure between two planets in the system rather than just a planet and the star. So another helpful angle that we've now gotten on this obliquity question is that I mentioned briefly before that we only had measurements of the projected obliquity of the host star. That's because the most common technique used to measure that can only measure the misalignment on the sky like this and not the other angle. And so seeing a misalignment in the projected obliquity can tell us a planet and star are misaligned, but it doesn't tell us exactly by how much. And there's now a growing sample of systems that either have been characterized with other techniques sensitive to that other angle, or that have measured rotation periods from a light curve where we can use that, the orbital period and the planet radius and the V sin I to get the other angle, the inclination. And so there's now a sample of about, I think it's like 50 planets that have a full obliquity measurement instead of just a projected obliquity measurement. And really surprisingly, most of these full obliquities that were measured tend to be at 90 degrees. So like polar misalignments, which is not something that we really expected in advance. And doesn't seem to be a selection effect as far as we were able to tell. So that's an interesting piece of evidence. And I bring it up now because this is true of hot Neptunes as well. So this is the full 3D obliquity measurement versus planet mass. And you can see there are misaligned, polar, perpendicular hot Jupiters and also hot Neptunes. So this is now maybe another piece of evidence saying that there's a common origins channel or channels for these planets. So thinking about, if we now run with this like perpendicular planets, what could cause that? There's a couple different explanations. There's not like a one that like is super obvious that that's what we'd expect, but I'm going to talk about one explanation that I've looked into recently and what implications it might have for hot Jupiters. So when we were talking about high eccentricity tidal migration before, we assumed just because we were starting with everything's like the solar system, the giant planets form far from their star, get put onto elliptical orbits out here at like a few AU, and then tidally circularize. But it could also be that the planets form closer in, like as warm Neptunes get put onto highly elliptical orbits and then undergo a final stretch of high eccentricity tidal migration. And one benefit of this that I recently saw from investigating is that this may be an explanation for how you would get a population of perpendicular planets. So here we have two simulations of a planet with an outer inclined companion getting put onto a highly elliptical orbit and then tidally circularizing. And if that inner planet starts out as a cold Jupiter, like we usually assume, this one I put it at 1 AU, in this scenario, which involves a dynamical mechanism called Kozai-Ledoff cycles, it's like cycles in eccentricity and inclination, the planet tends to end up at either 140-degree misalignment or 40-degree misalignment, not at 90. So on the face of it, that wouldn't be very compatible with these perpendicular planets. However, if you start out the planet a lot closer to the star, then the effects of general relativity become important, causing other precession of the planet's orbit and damping, or sorry, I shouldn't say damping, reducing the amplitude of the cycle that's exciting the eccentricity. It's okay that the eccentricity is not getting raised as high, since if it starts closer to the star, it doesn't need as high an eccentricity. And the general relativity also reduces the amplitude of the inclination oscillations. So then the planet can end up on a perpendicular orbit instead of being at 40 or 140 from the star. This is a mechanism that doesn't have a extremely high efficiency. It needs a companion that's already mutually inclined. And if we assume that there's all sorts of outer planets out there, only the mutually inclined ones would be able to do this. So we need some of the aligned planets to come through a different origins channel. So if this is at work, it would also point to the need for multiple origins channel. Another hint that maybe the high eccentricity tidal migration doesn't start out at a few AU, but a bit closer, as we're now amassing more and more planets with good eccentricity measurements. And this is a figure from a paper about a new system called TOI 3362b that has a high eccentricity. There's a recent discovery of this Kepler Neptune planet. And as we start to populate this eccentricity versus some major axis space, we're seeing a lot of planets. These are the planets we talked about before, the eccentric hot Jupiters. There's some eccentric warm Jupiters, but as we look beyond that at longer orbital periods, we're not seeing a lot of planets in that region. And of course, there are selection effects at work, but even when we account for the selection effects, we see an absence of highly eccentric planets out here compared to what we'd expect from theory. So this might point to planets starting their high eccentricity migration closer to the star. And that would require a first stage where they'd have to migrate close to the star or form closer to the star. Yeah, so let's take a look now at this second origins channel. I mentioned there's a need for a second origins channel that's not high eccentricity migration, disk migration, or in situ formation. One way to prove that is to look in more detail at systems like this and see what are the orbital dynamics there and do they point to one origins channel or another. And in particular, one type of, here, let's play this. One type of orbital signature that people have really tried to look for is orbital resonances. An orbital resonance is a period commensurability between planets in the system, just like we know about for Io, Ganymede, and Europa, the moons of Jupiter, where the planets periodically repeat their configuration. To technically be in resonance, you not only need to have these commensurate period ratios, but a resonant angle, which we're just going to talk about super quickly. I'm not going into detail of the dynamics, which is a function of the position of the planet and its longitude of periapse. That angle needs to be oscillating around one value instead of sweeping through every possible value. That's how you know a system's in resonance. And we want to look for orbital resonances because we know that to get into an orbital resonance, you need some sort of dissipation process, whether that's migration, other type of planet disk interactions like damping eccentricity, or tidal interactions. Here's our friend WASP-47, that hot Jupiter with 2 nearby companions. It's similar to a lot of warm Jupiter systems in that it's near a period commensurability with another planet in the system. But we don't actually know whether these systems are in resonance or just near resonance without more characterization. So I'm going to, I don't think I have too much time left, so I'm just going to mention we've characterized in detail this warm Jupiter system called TOI 216. And we found that it's in resonance, not just near resonance, but it has a pretty big amplitude of oscillation in that angle. And that implies that something more complicated than just plain disk migration happened, like a disturbance from additional planets, or maybe some other type of complicated interaction with the disk. So I'm now just going to spend 1 minute talking about the implications for planet atmospheres. So like obliquities, many processes can affect the atmospheres either before or after formation. The formation location relative to the snow line can change the atmosphere. The challenge is that snow line locations can vary by orders of magnitude depending on the disk conditions. You can have accretion of gas during gas disk migration or of icy planetesimals at the formation location. And so all of these different processes are affecting the atmosphere and making it a bit hard to disentangle what the origins channel is solely based on the atmosphere. Nonetheless, it's really interesting to try to look for links between atmospheric composition and orbital and architectural properties. So I'll end just by giving one example. So Singh et al. Found that hot Jupiters that they looked at tend to have water-rich atmospheres. This is really cool, but needs more interpretation to see which origins channel that's consistent with. It could be consistent with in situ formation, because if the planet formed inside the ice line close to the star, then the gas that would accrete would be very water-rich. But alternatively, the planet could have formed further from the star and accreted this water-rich gas as it migrated in. Or if it formed further out and underwent high eccentricity tidal migration, it could have accreted icy planetesimals near where it formed, ablated them in the atmosphere, and got the water in there that way. So this is an example of why more theoretical and observational work are needed to link atmospheres to origins channels. But I do think that will be a very exciting thing to work on as we learn more about planet atmospheres. So I'll leave you with this summary of different follow-up that would be helpful for disentangling these origins channels. Thank you.
Thank you so much for that wonderful comprehensive overview on hot Jupiters. We have plenty of time for some questions and discussion. So if you do have a question, you can either write it in the chat or you can raise your hand and I'll ask you to unmute yourself. I don't see any at the moment. I was just wondering myself, so in those cases where, from what I understood, if you had multiple planets in the system versus maybe one, then there can be different formation mechanisms at play there. Like, how large is the uncertainty in characterizing those systems where maybe we only at the moment just see one planet in that system, but maybe there is another planet hiding in the data that we just haven't been able to detect yet? Like, how large is that uncertainty in looking at the different formation mechanisms?
Yeah, that's a great question. Let me answer it in a couple ways. So I think the strongest constraint that's telling us that most hot Jupiters don't have nearby planets is a study from the Kepler mission that looked at the transit times of those planets and deduced that if there was a nearby planet, those transit times would not be perfectly periodic, and the planet could arrive early and late, which is called the transit timing variation. They did not detect any transit timing variations for any of the hot Jupiters in that sample. And because these were very deep, high signal to noise transits, there's not much that could be hidden right near the hot Jupiter. So that's kind of the strongest constraint that's telling us that there's at least many hot Jupiters that don't seem to have a nearby planet. That being said, Kepler hot Jupiters aren't all hot Jupiters. WASP-47 is a notable exception. It's also possible that Kepler hot Jupiters are different from more nearby hot Jupiters, and maybe those ones are more likely to have companions. We don't really know. So there's certainly open room for there to be hot Jupiters that do have companions, but it does seem like there's a pretty big population that doesn't. For the hot Neptunes, I think the constraints are weaker. The study I showed you was just showing that they don't have other nearby transiting planets, but if they have planets that are not in the same plane, we wouldn't necessarily see them transiting. And the transit time measurements for these hot Neptunes are not quite as precise. Those aren't as high signal to noise planets. So I think there could certainly be room for hiding somewhat nearby planets for those ones. So I think hot Jupiters, pretty clear that there's a population at least of lonely hot Jupiters. Hot Neptunes, it's not as clear and would benefit from more investigation. But there's clearly some difference between hot Neptunes and hot super Earths and Earths, and that they don't have at least nearby transiting other planets.
Great, thank you. I see you have a hand raised from Vatzel. If you want to unmute yourself, you can ask your question.
Hi, thanks for the great overview. You mentioned the bit about multiple planet systems and mean motion resonances, and I was wondering, what could you learn if you observe systems much younger, say less than 100 million year old, but already in such a configuration as compared to, say, much older systems where you see that?
Yeah, that's a great question. So that could help us identify which process gets these planets into resonance. So if it's disk migration, if that's the type of dissipation that's putting things into resonance, that would have to happen early on when there's still a gas disk around. If it's tidal migration, and when I say that, I'm not really talking about high eccentricity tidal migration, but just a modest tidal migration of something that raises tides on the star, like a close-in planet. That could happen over a much longer time scale. You could also have dissipation from forming the planet more towards the end of the planet formation process where you still have some leftover gas and planetesimals. That would be kind of an intermediate time scale, though I would say probably still shorter than a couple 100 million years. So being able to see planets that are already locked into resonance early on would be very consistent with disk migration or some other type of process that's happening during formation. That being said, you could also already have tidal migration at work then. So I think it would probably be more of a constraint, but probably also more of a surprise if we didn't see young systems with orbital resonances and then we did see them later. I don't think anyone's necessarily expecting that, but if that happened, that would be a lot more surprising and probably would point to something tidal capturing them as opposed to something with the circumstellar disk.
Thank you.
Great, and I think we have time for one more question. So Ilya, would you like to go ahead?
Very, very quick. You showed a plot I found really interesting, the distribution of the actual obliquity and not the sky projected one. And
yeah,
That's bimodality. That's because we don't see that in the sky projected value. So that's really interesting. Maybe you said it and I missed it. What is the color coding of the data points?
I need to remind myself of that. Actually, I can't remember. I can follow up and let you know. I think it's the projected obliquity, actually, because I think that's why these are all dark blue. Yeah, I think that's what it is. These ones are like, I think, near 180 in terms of their projected. So I think that's what the color coding is.
Okay, great. Thank you. I'll have to look up this paper. Excellent. Thank you very much.
Great. Well, thank you so much again for that wonderful overview. We're now, and just as a reminder, if anyone has any follow-up questions or discussion points, then you can move them into the Friday Slack channel, and feel free to ask any additional questions there to any of the speakers today. We'll be moving on to our next speaker, which is Joost Wardenier. And if you want to go ahead and share your screen, if you are.
Yeah, I'll go ahead and share.
He was going to be talking about understanding the iron absorption signal of the ultra-hot Jupiter WASP-76b using 3D modeling techniques. So whenever you're ready, you can take it ahead.
Yeah, thanks very much. Hello, good afternoon, everyone. My name is Joost. I'm a second-year PhD student at the University of Oxford. And in the following 15 minutes, I'll talk about simulating the iron absorption signal of WASP-76b. Which has been the bulk of the work that I did during the first 1.5 years of my PhD. So this presentation will mainly be based on a paper that we published back in June. So if you're interested in more background, I would definitely encourage you to check that out as well. So WASP-76b is an ultra-hot Jupiter. We've seen many of them being discussed today already, but just to briefly reiterate, ultra-hot Jupiters are the prime examples of exoplanets for which 3D effects are very important. Ultra-hot Jupiters are tidally locked, which means that they have a permanent day side and a permanent night side. And as a result of that, there's a lot of spatial variability across the atmosphere. So on the day side, the temperature is so high that molecules may be dissociated, metals may be ionized. But then on the night side, the temperature may be low enough for actual cloud formation to occur. Also, ultra-hot Jupiters are characterized by strong winds in the order of 1 to 10 kilometers per second. And mostly this wind profile can be decomposed into two contributions. Firstly, you have the day to night winds that blow material from the day side to the night side of the planet. And then under some circumstances, you might also have this super rotating jet that goes around the equator of the planet. Now, in the context of transmission spectroscopy, it's quite important to point out that ultra-hot Jupiters actually rotate by a significant amount when they pass in front of their host star. So in the case of WASP-76b, it's 30 degrees. And this means that if you look at the transit spectrum of such a planet, the observation really probes different parts of the atmosphere at different orbital phases during the transit. And also because transmission spectroscopy is really probing that limb region where the strong thermal and chemical gradients occur due to the day-night transition in the atmosphere, 3D modeling is really important for these ultra-hot Jupiters. Now, I prepared 2 slides on high-resolution spectroscopy and cross-correlation technique. I realize this has been covered extensively already today, so I'll move over that very, very briefly. So mostly when we look at a high-resolution observation, there's a number of contributions. First of all, we have the planet signal, there's a signal from the star, and also because we're doing this observation from the ground, we also have telluric lines. But the good news is that because the planet is rotating around the star, it's moving with respect to the star, we can actually separate the contribution from the planet from the other spectral lines thanks to the Doppler effect. And it's important to realize that even if we find ourselves in the rest frame of the planet, so when we correct for the systemic velocity and the orbital velocity of the planet, there may still be sources of Doppler shift left, namely planetary rotation and actual winds in the atmosphere of the planet. And those are the 2 sources that we'll focus on in this talk. Now, when you do high resolution spectroscopy, you basically distribute the signal of the planet over many different spectral bins. So that means that your signal to noise ratio in every bin is actually very low. So in order to really detect the atmosphere of the planet, you actually need to combine the information from many spectral lines simultaneously. And that's exactly what the cross-correlation technique does. So what you do is you take a template of spectral lines, you slide this template along the observation. So in this figure over here, the observation would be the black spectrum, which in reality is swamped in noise. And then whenever the lines in the template overlap with the lines in your observation, you get this nice peak in your cross-correlation signal. So the cross-correlation basically tells you two things. If you see a peak, it means that the lines that are present in your template were also present in the observation. So this is a way to detect different atoms and molecules in the atmosphere. And also the velocity shift at which the peak is situated tells you something about the average velocity by which the gas in the atmosphere is moving with respect to the observer. So moving on then to the iron signal of WASP-76b. This figure over here shows the cross-correlation map that Ehrenreich et al. Published last year. So here on the vertical axis, on the horizontal axis, I mean, we see the velocity shift of the iron in the atmosphere. And then on the vertical axis, you can see the phase during the transit. And the color map over here shows the cross-correlation signal. So you can see that at the start of the transit, around ingress, the Doppler shift of the iron lines is roughly 0 kilometers per second. But then as the transit progresses, the lines become more blue shifted until at some point the Doppler shift remains constant, and we get this vertical signal out in the second half of the transit. So yeah, this observation basically led Ehrenreich et al. To conclude that it may actually rain iron on the night side of WASP-76b, and of course it was a conclusion that resonated very well with the press. So here I collected a couple of headlines that I found on the internet. My favorite one is "Good luck pitching a tent on the exoplanet WASP-76b. The bloody raindrops here are made out of molten iron." So let's see what brought the authors to this conclusion. The bottom line is that gaseous iron is asymmetrically distributed across the day side of the atmosphere, as I'm showing here schematically on the right of the slide. So in these panels, we look at the equatorial plane of the planet. This is the day side. This is the night side. The day side obviously is much hotter than the night side. So due to the larger scale height, it's also more extended. And the panels over here show the distribution of gaseous iron across the equatorial plane of the planet. So you can see that initially at ingress, when the transit starts, the stellar light only penetrates the leading limb of the planet. On the leading limb, day to night winds blow iron towards the observer, but then the rotation of the planet points away from the observer. These two contributions cancel each other out, and you wind up with a Doppler shift around 0. But then as the transit progresses, the trailing limb rotates into view. The stellar light also penetrates the trailing limb, where both day to night winds and rotation of the planet point towards the observer. So your signal becomes more blue shifted. And then the idea is that at some point, iron on the leading limb of the planet rotates out of view, and your signal is purely dominated by the absorption on the trailing limb of the planet. So based on this observation, one may wonder, how do 3D effects influence the iron absorption signal of ultra Jupiters in transmission? And by 3D effects, we mean any spatial variation in temperature, chemistry, wind speed, irradiation, etc. So in order to address this question, we developed a 3D modeling framework, which consists of a number of components. So we start off with a global circulation model, the Spark MIT GCM, which we use to generate 3D models of the atmosphere of the planet. Then we plug the outputs of the global circulation model into a Monte Carlo radiative transfer code that was initially developed by L.C. Lee et al., but which we adapted for high resolution purposes. So basically what the Monte Carlo does is it randomly fires photons at a kind of disco ball configuration, which you can see here on the left. And for every photon, we basically compute the optical depth along the line of sight. And for every atmospheric cell that the photon crosses, we Doppler shift the opacities according to the local line of sight velocity. So according to the local wind speed and the local component of the rotation. We do this for 37 different stages, 37 different orbital phases during the transit. So we end up with 37 transit spectra, and then we can apply the cross-correlation technique to create this cross-correlation map. So just to give a short impression of what the output of the GCM looks like, of the global circulation model. So here in the top left, we have the temperature structure in the equatorial plane of the planet. The day side is obviously much hotter than the night side of the planet. It's also more extended. And as far as the iron abundances go, we can see that gaseous iron is more or less uniformly distributed across the day side. But then on the night side, the higher layers are depleted of iron due to these lower temperatures. Then as far as the line of sight velocities go, the top right panel over here shows the line of sight velocity due to winds. In this case, I plotted a model with atmospheric drag. So these different drag forces in the atmosphere, they can inhibit the formation of the equatorial jet. So here we only see day to night winds that blue shift the spectrum on both sides. And then when we include planetary rotation, you can see that the trailing limb of the planet becomes more blue shifted because it rotates towards the observer, whereas the leading limb becomes more red shifted because it rotates away. So these are a couple of spectra that were generated by the Monte Carlo code. So here in black, you can see the absorption lines you would get if you used a static atmosphere, so without any winds and rotation that can induce Doppler shifts. And then the green and the yellow line, they show the transmission spectra that you get when you include Doppler shifts at two different orbital phases during the transit. And you can see that really as you go through the transit, as you consider the spectra of different orbital phases, the line shape and the line positions, they are different. So to sum things up, it's the spatial distribution of iron, the 3D temperature structure, atmospheric dynamics, planetary rotation. All these effects determine the line position, the line shape, and the line depth. And these quantities, they vary as a function of time. So in order to make the interpretation of the spectra and the cross-correlation maps a bit more easy, we actually chopped the atmospheric annulus up in different limb sectors, as you can see in this panel over here. So we consider a trailing equator, a trailing pole, a leading pole, and a leading equator. And for each of these different limb sectors, we compute the cross-correlation maps. And because the cross-correlation is a linear operator, it actually turns out that the sum of these cross-correlation maps is equal to the cross-correlation map that you would get if you took the spectrum of the full limb. So this is kind of a way to decompose the cross-correlation map into different contributions that are easier to interpret and easier to understand. So if we look at these different cross-correlation maps, you can see that they are quite different for the different limb sectors. You can see that the trailing equator is most blue shifted because it rotates towards the observer. The leading equator is least blue shifted because it rotates away. And also you can see that the strength of the signals are not constant during the transit. So if we look at the trailing equator, for instance, the signal is relatively weak at the beginning, but then it becomes stronger as we go through the transit. And this again has to do with the day-night contrast of the planet. So initially on the trailing limb, we're probing a large part of the night side, but then as the planet rotates, the day side rotates into view, and the absorption takes place in hotter regions with a larger scale height. So this figure may look a bit overwhelming, but the structure is exactly the same as the structure of the figure on the previous slide. Only I'm showing here cross-correlation maps for 4 different GCM models that we tried. So the columns, again, they pertain to the limb sectors. And in this case, we show in the different rows, different GCM models. So we tried out a model without any atmospheric drag. Then we tried out 2 models with different drag time scales, 10 to the 5, 10 to the 4 seconds. And then finally, we also considered a model without any drag, but also without the opacities of TIO and VO, which are important absorbers in the optical. So if we look at the cross-correlation maps of the full limb, you can see here that I plotted the model in blue And then the white line here is the cross correlation signal of the observation by Ehrenreich et al. And the gray dashed line showed the full width half maximum of the observation. And in the first 3 models, you can see that the model actually produces blue shifts that are too small to really match the observation properly. In the final case, in the 4th model, you can see that the overall blue shift of the model is better, but the shape of the model signal is still different from the observation in white. So what I then did was to kind of try and modify the GCM outputs to try and see if I could improve the agreement between the model and the observation. So these are a couple of modifications that I performed. So in modification 1, I took the weak drag GCM model and I removed gaseous iron from the leading limb of the planet to create that asymmetry between the east and the west part. In modification 2, I applied night side temperatures to the leading limb of the planet. So I did not literally remove the iron, but because there are night side temperatures, the iron abundance has also become lower. And then in modification 3, I took the same model basically, but I applied uniform iron abundances throughout the entire atmosphere. From a theoretical point of view, this is an interesting scenario because it's simple, but it might not be physically plausible because in these regions where the temperature is very low, it's very hard for gaseous iron to persist because we're way below the condensation temperature of iron. And then in modification 4, I slightly increased the temperature on the leading limb to roughly 1800 Kelvin. And this is a temperature where gaseous iron may still persist. And as you can see, the scale height also becomes a bit higher in that case. So I think we can say that as we go from the left to the right on this slide, so from modification 1 to modification 4, we have a decreasing degree of asymmetry between the trailing and the leading limb of the planet. So this figure again shows the different cross-correlation signals that we find for the different modifications. And it's interesting to see that this time on the leading equator, you can really see that for each of the models, the cross-correlation signal really fades because iron rotates out of view. And then on the in the right column over here, you can see the cross-correlation signals that you get for the full limb. So the model again in blue matches the observation quite well for modification 1, and you can see that as we decrease the asymmetry between the trailing and the leading limb of the planet, this kink in the modeled signal becomes less pronounced. But I guess so I guess based on these models, we can say that we need a big asymmetry between the trailing and the leading limb of the planet, which could be purely chemical in nature, but it might also be that there's actually a strong temperature contrast. I think I'm going to skip over this slide for time constraints. There's a final topic that I want to touch upon, and that is computing KP-V-Sys maps from these cross correlation maps that we find. Normally, of course, when we compute a KP-V-Sys map, we assume that the atmosphere of the planet is purely stationary. But in this case, it might actually be that the CCF maps that we generated in the rest frame of the planet might actually emulate the signal of a planet that has a stationary atmosphere but a non-zero system velocity and a non-zero velocity semi-amplitude. So when we compute the KP-V-Sys maps for these cross-correlation signals over here, you can see that we sometimes wind up with peaks in the KP-V-Sys maps that actually have multiple maxima, which is quite interesting, and some of them are quite substantially displaced from zero as well. So for more information about the mapping between cross-correlation maps and KP-V-Sys maps, I'd like to remind you of BB Prinot's talk as well. And an interesting thing is that this diamond structure and this more complicated shape of the KP-V-Sys peaks has also been observed in reality. So these maps are from Nugroho et al., who studied iron absorption in the atmosphere of Kelt 20b, Mascara 2b. And you can also see that in some of these cases, KP-V-Sys maps, the structure of the peak is more complicated and is somewhat reminiscent of the structures that we see here. So this might actually be evidence for atmospheric dynamics going on in the atmosphere of this planet. Yeah, I'll skip over this one as well. Same story for KPV sysmaps. You can also decompose them into the signals from different limb sectors. And you can see that for each of the global circulation models that we computed, the KPV sysmap is nicely single peaked for the different sectors. But then when you add all these peaks up, you might actually wind up with more complicated structures. Yeah, so that brings me to the summary and conclusion. We've seen that interpreting high resolution spectra of ultra-hot Jupiters requires models that can account for 3D effects. So for spatial variations in temperature, chemistry, etc. We've also seen that the iron signal of WASP-76b suggests a strong asymmetry between the trailing and the leading limb of the planet, which may be either chemical or thermal. And also we've seen that the cross-correlation maps and the KPV sys maps can be decomposed into contributions from smaller patches of the limb, which could facilitate the interpretation and yeah, make it a bit easier to understand what's going on. Yeah, that was it. Many thanks for your attention.
Thank you so much. That was such an interesting talk. We do have just 1 or maybe 2 minutes if anyone does have a question. If you have a question, you can either raise your hand and I'll ask you to unmute yourself, or if you prefer, you can write it in the chat. Are there any other planets that this kind of similar process of characterization may be interesting? There's been a lot of discussion about WASP-76b, but are there any other interesting up and coming planets that we maybe do some similar analysis with?
Yeah, I think there's quite a reasonably large set of ultra-hot Jupiters and hot Jupiters that will be studied more closely with high-resolution spectroscopy. I think also for WASP-121b, a kind of asymmetric iron absorption signal has been observed already. Yeah, so I think definitely in the coming 1 or 2 years we can expect more of these asymmetric signals to pop up. I think definitely for ultra-hot Jupiters.
Awesome, that's exciting. I don't see any raised hand. Oh, yeah, Neil Gibson, would you like to go ahead and unmute yourself?
Sure. Hey, Joost, great talk. Really interesting stuff. I'm just kind of curious about, I mean, these 3D effects are kind of a bit terrifying for people like myself that, you know, are just working with these very simplified 1D models. But is there any way you think we can do simple modifications to our 1D models in order to retrieve something interesting for you guys to sort of interpret the 3D models and more accurately, I guess?
Yeah, I think in many cases, and I think this especially goes for emission spectra, I think you can already get pretty far in like, yeah, trying to mimic 3D effects just by averaging over the spectra from multiple 1D models. I think for transmission spectroscopy, it might be slightly more difficult, because I think as you go through the transit, you really probe different parts of that thermal / chemical gradient. But yeah, I think it certainly be interesting to look and find out how we can use 1D models to in an optimal way to kind of try and see if we can interpret the 3D effects. Yeah, because I agree, it's not going to be feasible to use Monte Carlo spectra for all the data analysis.
Yeah, absolutely. Thanks.
Okay, I think we'll head off to our break now. I do see that there is an additional question in the Zoom chat, but maybe you can move that to Slack or
yeah, I'm happy to answer
chat.
that on Slack.
Yeah, great.
Thanks.
So we will reconvene at 4:40 p.m. Central European time. Sorry, I'm just very confused because I'm in the US, so trying to look at the clock. So in 13 minutes from now, so everyone go and grab a coffee and stretch and have a break, and we'll see you back here at 4:40.